Hi, everyone. This is Charles Hoskinson broadcasting live from warm, sunny Colorado. Always warm, always sunny, sometimes Colorado. Every now and then something comes up that is super freaking cool. And it's the result of just a brilliant, long, brutal slog. And I have to hand it to Microsoft. They've done something so absolutely remarkable and incredible that I wanted to make a quick video. I'm going to spend quite a bit of time looking through this. And actually, the paper here is very dense and very hard to read, but quite interesting. So, this is the paper here. So, basically, what Microsoft did is they figured out how to build a topological quantum computer. Okay. And what we're going to do is we're going to format the background a little bit, change that to squares. That's a little easier to see. A topological quantum computer. This is a long theorized but impossible to build thingy. I like the word thingy. So, in general, quantum computers, they have these different states. And when you look at these different states, they allow you to kind of get a sneak peek at a large, expensive calculation, and then it gives you some clarity on how to solve it. And that sneak peek is efficient. And so as a result, there's all kinds of categories of things which make these super useful to society. For example, you want to break cryptography. You want to like make matter. So you want to simulate biochemistry or or chemistry in general. There's all kinds of things in weather prediction, et cetera, astronomy, blah, blah, blah. Long and the short is, if you can build one of these things that give you the sneak peek capability, super fucking useful because a lot of the calculations that you'd want to do in these categories, they take more than the time in the universe to solve. So for the cryptocurrency industry, we care a lot because you could break the cryptography of cryptocurrencies, most of the crypto we use, but not all. Like, for example, Starks are immune to quantum computers with a quantum computer because that sneak peek is useful for solving the discrete log problem. Okay, now, what the hell is this whole topological thing about and why is it interesting? So, in general, the power of a quantum computer is called a qubit, and more is better. So as you go up in the qubit range from 1 to n, you start getting the capability to solve these problems. The problem is that as your qubit count goes up, there also the rate of errors goes up, and those errors destroy your calculation. So eventually you reach a kind of a threshold, and that's currently, I don't know, it's somewhere around a few hundred of qubits, which is not particularly useful for where we want to be. And there's physical and logical qubits and all kinds of things beyond the scope of the video, because we'll keep this brief for the moment. So, everybody in quantum computing land has been trying to figure out a hardware approach, and some of those use photons. It's called photonic quantum computing. Others use trapped ions. Then this topological is another one of those approaches. Here's what makes it interesting, and it shows you the dogged determinism of Microsoft. They spent 17 years on this, 17 years, an enormous amount of time. They basically first did something called molecular beam epitaxy, which is a top shelf, high end way of building semiconductors. And so basically, it kind of looks like this. One of these days, I'm going to learn how to draw so I can actually make nice pictures. You build a chamber, and that chamber has pumps in it that make it a vacuum chamber, and then you have these effusers inside of it. The effusers, You have a little substrate here, usually a crystal, and this is cryopump. Okay, I'm going to turn this off up here because it's messing up my writing. Cryopump. And you shoot atom by atom materials at this vacuum chamber, and it grows a thin film, atom by atom, of whatever the heck you want, typically at a rate of about 3 micrometers. There we go, per hour at most. So super fucking slow. So what this allows you to do is basically build any exotic material that you want. So what Microsoft first did is they took indium and they took arsenide, typically used in the semiconductor industry. And then, you ready for this? They blended it with aluminum, which is used in the superconductor business, and they created kind of a hybrid exotic material, and they call this a topo capacitor. And the only way that you can do to build this topo capacitor, or topo conductor, I should say, that's the terminology they're using, topo conductor, topological superconductor. The only way you can build it is with one of these molecular beam epitaxy devices. Super expensive, super slow, and it basically has to be built atom by atom. This alone is pretty fucking hard to do, you know, and this is what your guys at TSMC or these other fabs are kind of really smart about, like top shelf superconductors. Okay. Then they configured it in a way where they took these things and made nanowires in kind of like a U-shaped configuration, these little nanowires, and they combined the nanowires with stuff that's in your TV, quantum dots, and a little microwave reader. Okay. And here's where it gets crazy. They using a super cooled apparatus, and so typically it's a helium-3, helium-4 diffuser, because it has to get super cold, basically absolute zero. You freeze all of this shit in a chip, and then use a magnetic field, and if you do it just right, you can create a brand new particle that doesn't exist in nature. It's called a Majorana fermion. And what so normally every particle, it has particle, and then there's an antiparticle. And so there's this duality of nature. Well, a Majorana Fermi particle, its antiform is identical to its form. So it's like a half particle. Okay. Now, why do you do this? Because what you can do is you get non-locality for your qubits. That's a big, scary word, and I'll break it down for you. The non-locality basically means that the qubit um, is both parts have to be fucked with for the computation to fall apart. And even if one of these parts gets hit, which is all the time, that's why you try to make it as cold as possible with your helium diffusion or whatever you're using. The other part has to be hit too for the thing to fall apart. Wait a minute here. If I can do that for two, eventually I can do it for n pairs. And that's called the Majorana surface code, and it was invented around 2015. Surface code. Okay, what does this mean? It means that you have a stackable way to be able to exponentially reduce the error rate in a computation, and this technique can be used to put many of these U nanowires together in a single chip. And if you're measuring these quantum dots, which are in your television, we're pretty good at that when they entangle. You can use microwaves to read the output. So you have a super accurate way of measuring state. Okay. So all this techno babble, what does it mean? It means that I think Microsoft has a scalable platform for a real quantum computer. Um, they invented a brand new way of making basically a brand new material. It's the very first topo conductor. It's a new state of matter that they invented just for this. They had to basically create this atom by atom. So talk about that. That's just fucking crazy. Then they had to figure out how to put it into a chip and manufacture a chip in a very, very specific way so that they could stack things like this. Then they had to figure out how to get magnetic fields to be just right to create what are called MZMs, Mariana zero modes. So basically, you create these quasi particles that get entangled and they share state. And then, they had to figure out how to build this material in a way that it has a project it has a property called, a topological material. So, you have these braided wave functions, so they resist changes. It's almost like putting Teflon on the surface of pan, things don't stick to it. You basically prevent stuff from disrupting the calculation. Then they still had to figure out how to cool it, have all that stuff work at near absolute zero, and that's what the aluminum is doing. It's a superconductor inside the thing, means there's no resistance that comes through. Okay, so I had to put all of that stuff together, and then they figured out how to read it. So they had to figure out how to link it with quantum dots and microwave reader. Okay. Then they had to write a programming language for it, which they did, Q sharp. And so they have an actual programming language today that you guys can look up and use it. And then they had to figure out how to deploy it. So they're going to put it in Azure. Papa Sacha. Holy shit. This guy's on fire. Billions of dollars in 17 years of R&D. So, whenever you do stuff like this, like you invent a synthetic fundamental particle, quasi particle, you invent a new material, you invent a new programming language, you invent a new chip, a new paradigm, it's a little rough. But I look at this as like the invention of the transistor. When Bell Labs created the transistor, vacuum tubes ruled the roost. They were very, very pervasive, and transistors actually did not outperform vacuum tubes. But within just a decade, it became blatantly clear that transistors were the way to go because they had a property of low cost scale. Quality kept going up, cost kept going down, and density kept going up. You want these properties for a paradigm. These U wires, you can stack lots of them inside the chip. So you got density. MBE can be modified into different techniques for mass manufacturing. So this is more of a research process, but there's ways to make something custom for this. So cost will go down, and they're going to learn as they build iterations of the chip very rapidly how to improve the qubit count and the quality of yields for the thing. So I think the topo-conductor concept has the very same properties as the transistor for quantum computing. It's pretty remarkable, and it's plug and chug into their quantum computer. Now, I'm a big fan of the photonic approach because you don't have to cool them, or at least in the core system. If you look at Xanadu's systems or others, but they never quite cracked something like this. So it's an incredible day for Microsoft. It's I've never seen anything like it. The Ettore Mariana, an Italian guy, he was the one who came up with this a century ago and predicted it. By the way, he also disappeared mysteriously, just like the fermions, right? And nobody thought it was real, and everybody said, "Oh, it'd be really cool if we had something like this." And it's like the peanut butter and jelly, a topological superconductor. You need the superconductor to operate these things. That's kind of your entry condition, but the topological properties create those braided structures that are very resistant, and so they protect it. And then the stackability of this non-locality is really what's cool. So this Majorana surface encoding is pretty cool stuff, because you can put the end pairs together potentially, and they're going to figure that out. They're going to crack it. So very early days, but this is a monumental achievement, absolutely remarkable achievement for the topology for quantum computing in general. So, what does this mean for Cardano? Well, the good news for you guys is that Cardano's research headquarters is University of Edinburgh, which is also a world-class university for quantum computers. So right now, the giga brains there who know far, far, far more than I do about this, they're going to take a look and deconstruct this, and we'll try to develop a horizon of what we think it's going to take to actually productize this, if it all is possible. And Microsoft, they have to show some more. There has to be some reproducibility in this, although they claim the chip they've created already actually has these, and it's running at 8 qubits. So that's interesting. But in general, we need to speed up a little bit our post-quantum hardening for Cardano. We have a group of people who think about these things, and there's different techniques like hash-based crypto, lattice-based crypto, and others that make your crypto immune to quantum computers or resistant to them. But in general, the reason why we haven't embraced them is A, there were not good standards yet, and B, typically these are about 5 to 10 times slower and 5 to 10 times larger in terms of transaction size to use post-quantum. So we know how to do it. It's just, we haven't really embraced it because we're waiting for optimizations to come and standardization to come. Good news is that NIST has standardized these things. And we now actually have a suite of them, and there's a lot of new capabilities coming on. So in the budget, we're going to add a proposal for accelerating the post-quantum hardening scheme and adding new capabilities and features to Cardano. And this can be done in the 2 to 3 year horizon. I do not believe Majorana is going to be product ready within 2 to 3 years. I don't think this is going to create like the tomorrow thing. It's just going to basically create a revolution with a new paradigm of quantum computing. And a lot of people are going to start working on topo-conductors, and you're going to see massive improvements. The TSMCs of the world can do this far, far better than Microsoft can. And the fundamental physicists are going to get really curious in this, and they're going to massively improve the design. And now that these things are real and they see them, and Microsoft is certainly going to work with partners to figure out all of these different mechanics. So 5 years we have a problem. 10 years we certainly have a problem, but 2 to 3 we won't. So we need to model basically a quantum adversary. So rewrite the papers from the perspective that the adversary has a quantum computer, and then work our way backwards. So post quantum VRF, post quantum Ouroboros, post quantum signatures. That's what most people say when they're quantum resistant. And then also take a look at the hash algorithms and say, are we okay with hashes? Probably are. Grover's is not a problem there. But holy shit, guys, pretty crazy when you think about it. So a lot of post quantum work we got to do now. Thanks, Microsoft. It made my life a little harder. On the other hand, it's pretty magical what you can do with all this. As a final point in the video, they released something recently called MatterGen. And MatterGen is a large language model for material science. And you just tell it what you want, and it kind of figures out how to make it, how to build things atom by atom. You pair MatterGen with a quantum computer, you could basically do miracles. You can say, I manufacture cars, and for my engine, I want the following properties. It melts at this point, and it bends with this, and it bonds with these materials, and blah, blah, blah. MatterGen with a quantum computer would just sit and think about that stuff and come back to you with a recipe and tell you how to make a new material that's never existed before, which is perfect for what you're looking for, and tell you how to make it at scale. It's just insane. Absolutely insane. It's literally a God creation kit, when you think about it. And same for biochemistry. I have a biochemistry group, a biotechnology group, and there's this one thing, these plasmids, and basically they make any chemical you want, and a company called Minicircle uses them, amongst many, many others. They've been around for a long time, and they're right now using them to make follistatin, and the follistatin is used to build muscles. So it's like the muscle pig stuff. So they give you the plasmid, you build a lot of muscle. In some cases, 10 to 15 pounds of muscle. It's pretty cool. Well, what if I tell this MatterGen model, hey, you know what? People got microplastics in their body. And those microplastics, I want you to invent a molecule to bond with them, and that molecule will be water soluble. Okay, what does that mean? It means that you just pee out your microplastics. It detoxes your entire body. And I can then make that in a plasmid inside your body, inject it, lasts for a year, has an on-off switch. The mini circle ones do. It's pretty cool. Well, okay, the model just tell me how to do that. And I'll say, oh, by the way, it can't bond with anything else. So it's chemically inert to your body chemistry. So it creates no side effects. How about that? Just fucking nuts. So that's what this does. It's gonna change everything. It's absolutely going to change everything. And when people say move fast and break things, Microsoft, a $3 trillion company, they proved that the opposite paradigm is prudent. 17 years they worked on this. 17 years. Think about that to create a topo-conductor. Congratulations, Microsoft. You knocked this one out of the park.